In 1958, the moment humans first detected Earth's radiation belts, they realized they'd been living inside a shield, and leaving it meant stepping into an invisible killer. For 4 billion years, our planet's magnetic field has been deflecting cosmic radiation. We evolved under this umbrella without knowing it existed. Then on August 26, 1958, Explorer 1 crossed into space and its instruments went haywire. The sensors were being hammered by something invisible, millions of high-energy particles trapped in rings around Earth. Van Allen radiation belts, they'd later be called. And everyone involved in the space program had the same unsettling realization at once. We've been living in a bubble. Step outside it and you're exposed to something we barely understood. The astronauts training in those early years didn't know the full picture. NASA had the data from Van Allen's instruments, but the implications were still being calculated. How much radiation was actually dangerous? How much could a human absorb before damage became irreversible? The answers weren't clear. And so, in the late 1950s and early 1960s, astronauts were being prepared for missions into an environment whose hazards remained partially invisible to even the engineers sending them there. By April 1961, Yuri Gagarin became the first human in space. His capsule climbed through the Van Allen belts in roughly 10 minutes. The radiation dose he received was significant, around 50 to 100 rem depending on the trajectory. To put that in perspective, 50 rem is enough to cause radiation sickness. Gagarin survived, but the Soviet Union kept the radiation data classified. They didn't publicize what their instruments had recorded. The Western world wouldn't fully understand his exposure for years. The American Mercury program followed months later. Alan Shepard's suborbital flight in May 1961 kept him below the densest part of the radiation belts, relatively safe, but NASA planners knew that longer missions Earth orbit, the Moon, would require passing through those belts multiple times. Each pass meant cumulative exposure, and no one yet knew the long-term consequences of accumulating that kind of damage at the cellular level. Here's what NASA radiation physicists understood by the mid-1960s. Cosmic radiation comes in two forms: solar radiation particles from the sun, usually manageable but occasionally spiking in dangerous storms, and galactic cosmic radiation, high-energy particles from deep space, accelerated by distant supernova, traveling at nearly light speed. These particles punch through spacecraft like bullets through paper. They don't stop at aluminum, they don't stop at water, they don't stop at skin. When a high-energy proton or heavy ion smashes into human tissue, it doesn't just burn. It ionizes atoms, rips electrons away from molecules. That creates a cascade of chemical damage. DNA strands break, proteins denature, mitochondria malfunction. The cell either repairs itself, mutates, or dies. Over time, repeated hits to the same tissues can cause cataracts, central nervous system damage, and cancer. And unlike a wound you can see and treat, radiation damage happens invisibly at the molecular level. By July 1969, when Apollo 11 launched toward the Moon, NASA had made a calculated bet. The astronauts would spend about 5 days in transit, 3 days each way, plus time in lunar orbit. That meant passing through the Van Allen belts twice at speed. The trajectory was designed to minimize exposure time, but the belts were unavoidable. Neil Armstrong, Buzz Aldrin, and Michael Collins received roughly 1 to 2 rem of radiation during their journey. Again, survivable, but the risk was real and it was accepted. The Apollo missions kept piling up. 12 astronauts walked on the Moon across 6 landings between 1969 and 1972. Each one received radiation doses that, by modern safety standards, would be considered occupational hazards. NASA tracked the numbers carefully, they had to, but the full health implications wouldn't become clear for decades. And that's the dark part of the story that wasn't widely discussed at the time. No one knew if these men would develop cancer, suffer cognitive decline, or face other long-term consequences from their exposure. Fast forward to the 1980s and beyond. NASA long-duration missions, Skylab Space Shuttle, the International Space Station, kept astronauts in low Earth orbit, where the radiation belts are less intense but still present. Astronauts spending 6 months aboard the station receive roughly 50 to 100 rem annually. That's in addition to cosmic radiation exposure. Over a career spanning multiple flights, an astronaut might accumulate 1,000 rem or more. The risks compound. Today's astronauts are screened for radiation sensitivity before they fly. NASA monitors their cumulative exposure. There are career limits, thresholds beyond which an astronaut can't fly anymore because the statistical risk of cancer exceeds acceptable levels. It's a grim calculation. Weigh the benefit of the mission against the probability of harm. And for long-duration missions to Mars or beyond, that equation becomes almost impossible to solve. A mission to Mars takes 6 to 9 months each way. Astronauts would pass through the Van Allen belts, then spend months in deep space where galactic cosmic radiation is unshielded. Current estimates suggest a Mars mission would expose astronauts to 300 to 1,000 rem over the course of the journey and surface stay. That's enough to increase cancer risk by 1 to 3% for some astronauts. It might mean trading decades of life for a few weeks on another world. Engineers are working on solutions. Shielding materials, polyethylene, water, even hydrogen-rich polymers can reduce exposure if placed strategically. Active shielding technologies are being researched, using electromagnetic fields to deflect charged particles. Pharmaceutical interventions to boost cellular repair are in development, but none of these solutions are perfect, and none of them change the fundamental truth: beyond Earth's magnetic shield, space is hostile to human biology. The astronauts who flew in the early space age, they made their choices with incomplete information. They understood the risks in broad strokes, but not in detail. They flew anyway. Some of them are still alive. Whether their space exposure has contributed to health problems remains an open question. In many cases, radiation damage can take years or decades to manifest. The gap between what they knew then and what we know now is sobering. As we plan for deeper space exploration, lunar bases, Mars missions, asteroid mining, we're running out of time to solve this problem. Every year we delay is a year a potential astronaut doesn't get to fly. Every year we wait is a year we're not building the technology that might protect them. The radiation threat isn't theoretical anymore. It's the limiting factor in human spaceflight, and it's a conversation we need to have openly. The story of radiation in space isn't one of triumph or failure. It's a story of calculated risk, incomplete knowledge, and the price of exploration. It's the untold part of every space mission, the invisible threat that shaped decisions, limited missions, and sometimes changed the course of human spaceflight. The next time you see an astronaut floating in orbit or walking on the moon, remember, they're not just brave. They're accepting a dose of harm that we're still trying to understand. Subscribe for the untold stories behind every mission, the decisions made in silence, the risks no press release mentions, the science that changed everything.